statements, we can then say, okay, if this one is, if this statement means the same thing as this, they're logically equivalent. And we can also determine, are they consistent? Consistent means that they're both true at some point on the same line, which bar A plus bar B is consistent at least on one line with the other one. We have a term inconsistent, which means there's never a line in which they're both true on the same line. And then there's logically contradictory, which means on every line, if this one's false, this one's true, and if this one's true, this one's false. And that means logically contradictory. So you compare them, and you get those titles, those labels, are really nothing that particular. They're just, they're just labels, right? You can just look at them and see. If I ask you, is this logically equivalent or not, you can just look at the definition and say, well, did they come up that way, right? But the thing about it is if I give this on a test and you get one of these T's or F's wrong, it will change that answer. And that is where the problem lies, which is why it's good to practice a lot. And I can tell you just honestly, if I were to sit down and do this, I don't know why I would, because it's not that much fun for me. If it was 128 lines, absolutely, but not one of these 16-line problems. That's not fun at all. But if I get a fun 128 line one, wow, that'd be a good Saturday afternoon, right? But the case though is I wouldn't do this. But if I did do it and I was doing it for a test, I'm sure I would mess something up along the way. I'd get a T or F in the wrong spot. I'd mess it up, and that's just going to happen. I mean, there's just no more to say about it. Okay. So. Let's just do one more of these from this section, and I'm going to glance through the other part, and I'm going to talk about validity. Am I almost out of overheads? Oh my goodness, what will I do? I'll have to go get one of the other 500. I could also clean one. I could also work. So number 5 is Q, horseshoe, P plus Q, right? Is that right? Yep. So how many lines do I need?
No, 4.
4, right? That's the reason I wanted to use it, because it's a little bit of a trick question, right? Yeah. There's 3 letters here, but 2 of them are the same. So there's only 2 unique letters, right? There's only 2 unique letters. So 2 to the power of 2 is 4. So we're going to do T, F, T, F. Now, I always think it's best to just go ahead and go over to the Q and do it as TF, TF. You need to make sure they match, because if they don't match, then you're not really doing the right problem, okay? And then TT, FF. And then true plus true is true, true plus false is false, false plus true is false, and false plus false is false. So it's TFFF on the part of the parentheses. Then you do the horseshoe. And that's true. False horseshoe false is true. True horseshoe false is false. And false horseshoe false is true. So it's TT, FT. Okay?
Yes.
And the only reason I wanted to use that example was just to show you if you have 2 Qs. Now, what you can do with this is you can then use this. The other way you can do it, besides looking at statements themselves and classifying them as tautologous, self-contradictory, or contingent, meaning the value is going to vary from line to line. Or comparing statements and finding ones that are logically equivalent, logically contradictory, or consistent or inconsistent. Those are our 4 labels there. The other thing you can do is you can use this to test validity. And the way you test validity is a valid argument will be an argument in which if all the premises are true, the conclusion necessarily must be true. So the way you test validity is you find a line in which some of the premises, all the premises are true, but the conclusion is false. If you can find that, you will prove it is an invalid argument. And that's what makes it a little bit weird, because you're looking for that, and when you find that, okay, I found it. And so your natural inclination is, okay, it's valid. But in fact, you found it's invalid. You're proving that it's invalid, not that it's valid.
So
valid is just sort of by default, it would be labeled valid.
Is it really a simpler way to do it if you do it the indirect way?
I'll show you an example of that here in just a minute, okay?
All right.
So let's just do one example of this. So with logic, like what you'll find in the book is, it's in chapter 6. I'm going to go look at some of the book has translations where you have to translate these things. And that's where I'm in this second chapter, I don't think I have you do any translations on the test. Because I think that's probably asking. What's that?
That knocks out my problem that I was having.
With the first module you have to, with the second module you don't. Okay. So one thing I want to mention is in the book, if you go in the book, you're assigned to do 6.3, 6.3 A and B. That's asking you to find equivalent and tautologists and self-contradictions, and they use a little bit different terminology, but that's all that is what I already talked about. And then 6.1 and 2 are asking you to do truth tables that are going to be direct and indirect. And so if you look at it here, number 21, what did I... Oh, I did require you to translate these. So it's an argument like number 1, 6.1, number 1 is if people know... If people know what is right, they will do it. So it's K horseshoe D, right? And then the next premise is, but people do not know what is right. So bar K, they don't know what is right. Therefore, they do not do it. They have this little 3 dot thing. That means therefore in the book. If you see that ever, you don't have to put it on your table, but that's separating the conclusion. Sometimes you'll put that so you know where the conclusion starts, the 3 dots. In some logic books, they'll do a slash and then a double slash. However you want to do it, I don't care. But you know, this is your conclusion. That's just indicating that's where the conclusion is, the 3 dots. Okay? So, how many lines are we going to need to do this?
4.
4 lines, right? Because we have 2 letters. So it's going to be true, false, and then same thing on this other one. Go ahead and do it with the K while we're at it. And D is going to be true, true, false, false. And the other one's going to be true, true, false, false. Make sure the D's and the K's match, right? Okay. Now what happens is we can do the bars in front of them, so we can go false, true on the K. Okay, we can kind of circle that. That's premise 2. And this conclusion is false, false, true, true. We can circle that. And then this one is true horseshoe true is true. False horseshoe true is
True.
true horseshoe false is,
False.
and false horseshoe false is true. So we circle that. So what we're going to do is we're going to say, well, on line 1, do we have all true premises? No. So we don't care what the conclusion is. On the next one, oh, we do. There's 2 true premises. Is the conclusion false? Oh, in fact it is. So what we do is we circle those T's and that F on that line, and we then say this is an invalid argument. And does it happen again? No. The last one, you have true, true, true. But the case is in time. There are times where it's a true argument, but it is not always that way. So therefore, it's invalid. Now, this is what we call, and it's one of the things you have to look for your logic project. This is what we call denying the antecedent. And what happens is just because the antecedent isn't true doesn't mean the consequence isn't true. Sometimes people think that. They say, well, what was the argument? If people know something, they'll do it. They don't know it, therefore they don't do it, right? Well, that may, the problem is people sometimes do stuff even though they don't know it, right? They just do it by accident or just for no reason, they just do it, right? And so that's the case is, just because you know it, you do it. Well, you can do it for other reasons. Not knowing does not prove that you don't know it. It just It doesn't mean you won't do it. It just means you don't know it, right? And so that's called denying the antecedent. So the case there is like, if we were to go back to our assassination or our punishment, you know, if the K was, if you stay out after curfew, then you'll be grounded. You didn't stay out after curfew, therefore you're not grounded. That's denying the antecedent. Just because the antecedent isn't true doesn't mean the consequence isn't true. Questions or comments? Are we happy? Now, let me give one example of the indirect method. But what would happen is if this had been just K instead, if it had just been just the letter K, this is actually what we call modus ponens, and modus ponens is a valid logical argument type. And what would happen if it was that is this would be true, false, because that's the way we did it. And we would find there's a true premise. Wait. Oh, that would have to be not bar D, it'd have to be just D, I'm sorry. Let me do that, take that out as well. Okay. So if you did that, it'd be true, 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 false, 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 true, false, and then true, false, false. There's only one line in which all the premises are true, but the conclusion is true as well. Okay? So we couldn't find anything in which the premises were true and the conclusion was false, so it is a valid argument. This K horseshoe D, K therefore D is a valid argument called modus ponens, and it's logically, it is a logically valid argument type. Okay, you have to find examples of that too if you really want. So let's give one example of the indirect method. If we turn our book, let's just find one of these examples. I don't know if it's valid or not, because I am going to be working from it the same as you are. So let's go with number 13. Why? Because it's a lot of lines if we were to have to do this whole truth table, right? So line number 13 says, premise 1 is M plus N. Premise 2 is bar M plus L. Premise 3 is bar P horseshoe bar L. And the conclusion, I'm going to just do it down here, not because that's the way to do it, but because I'm running out of space. Okay? Can everybody follow that? Is it okay if I do that? The conclusion will be P plus N. So what happens when you do the indirect method is what you do is you go through and you say, let's assume all the premises are true and the conclusion is false. Okay? So we're just making that assumption. Does that make sense? Because that's what you have to do to prove invalidity. Okay. So if we did that, then the only way for this to be true would be if M and N are both true, right? So we would go true and true, which means any other N's are going to have to be true, and any other M's are going to have to be true. Okay? Fair enough? And so, well, in order for P plus N to be false, if N is true, the only way that can be false is what? For P to be false, right? That's the only way that will be false. If N is true and P is false, right, then plus would be false. Does that make sense, Gracie? I can't see you, so I don't know if you're actually...
I'm doing a confused face.
Okay. So what happens is we've already assumed N is true, and we know that plus has to be false. So the only way for that false, the only line in which, the only way it could be false with one of the conjuncts true is for the other conjunct to be false, right? Well, look at your chart, the little table. If you look at your little table, right, the table says, you know, A plus B, it's T, T, T.
Which 13 are we doing?
What's that?
Which one are we doing? I'm sorry.
That's what I did. I didn't know it was 13 either.
If P was true, like this, if you had this, where this was true and the other one was true, does that make sense? Like looking at this first line here?
I can't even see what you're pointing to.
Okay, I'm sorry. If if B is true,